Morning, kids. What's going on? Hey, let me share my computer screen with you. Give me a second. Hopefully, it will come up in just a second.
See?
I'm teaching from home today, so I've got my little son here with me. He's probably going to make some noise. I apologize. Say hi.
Hi.
He's 3. All right. Let me know if you can see my computer screen. It should be coming up. Not yet. Give me a second. Oh yeah, no, I get it. All right, here we go. Remind me later. Run the big blue button applet. LLL. Start sharing your desktop. Okay. All right, we good? Are we up?
I have your armpit.
No, you cannot have my armpit. Okay.
Can I smell your armpit?
You cannot smell my armpit.
It's this?
Like I said, I have my 3-year-old son with me, and he's asking me to smell my armpit. I don't understand 3-year-olds either.
What are you talking for?
I'm talking to the students.
Students.
Yeah, the students. All right. So check this out. Yeah, no, I have to. No, I'm not at the school. I'm teaching from home today. Today's my off-site work day, but I did want to make sure I ran a class for you guys. All right, so here, can you take him? I gotta run the class. All right. How's the audio coming through? Shh. Really bad? I'm doing the best I can.
Daddy.
Audio check. Audio check. Is it better now?
Daddy.
Audio check.
Daddy,
Griffin, you gotta go outside.
Daddy. Mom, I not play Legos.
Okay. Well, you have to go outside. I'm running the class right now. Sorry, that's my 3-year-old son. He is adorable, but difficult to run a class with. Yeah, he is absolutely adorable. Anyway, let's get this party started, if that's all right with you guys. His name is Griffin. All right. I have a 3-year-old brother. Awesome. So I'm going to start up our class. Let's get this thing started. Okay. Can you hear the audio? It's coming through all right? All right, let me know. Let me know if it's tough to hear. I'll slow down. I don't have all the resources available to me at home as I do at school, so I'm kind of going to be lecturing kind of out of the book today. I'll try to go through it pretty systematically, and hopefully this, will all make sense to you. Cool? So the first thing we're going to talk about is we've been talking about the cell. And right now what we're going to be doing is we're going to be talking about movement within the cell. And how do things... So every kind of cell, whether it is a... well, let's see. I explained to you that there were 2 different kinds of cells. One is a prokaryotic, and then the other one is a eukaryotic. The eukaryotic... Audio check. Audio check. Is it any better? All right. I'll try to do this as best as I can. I'll try to go as slow as I can. Please, I really hope that it works. I guess my internet at home isn't as good. Okay. So there's 2 different types of cells. There's the prokaryotic cell, and there's the eukaryotic cell. We've been studying the eukaryotic cell because that one was more interesting. The prokaryotic cell, that's basically the big difference is it doesn't have a nucleus. And it's got a lot less things going on in there. It's mainly talking about bacterias and archaeobacterias, so we don't really talk too much about it. But one of the most important parts of either of these cells is they both have a cell membrane right there. They both have a cell membrane. And whether we're talking about an animal cell, a plant cell, or a prokaryotic cell, they all have a cell membrane, which is basically this protective coating on the outside, that the outer coat of the cell. Now, one of the things I was thinking about is the screen door. Do you guys have a screen door at home? You know, it's like you open up the door, the big wooden door, but there's still a screen door. Do you have that at home? Yeah, all right. Now, what's the point of that screen door? Like, why do we have the screen part of the door? It keeps the flies out. All right, yeah, exactly. There we go. It keeps the flies out, absolutely. It keeps the flies out, but it lets the air get in. So it allows certain things to come in, but it keeps other things out. Yeah, and what I like about it is it nicely allows the air to come in and the wind to flow through it, but it keeps the bugs and the flies and the cockroaches all outside. So that's kind of what the cell membrane does for the cell. It's like the passageway. It's like a big screen door around the entire cell. And the cell allows certain things to come in and certain things not to come in. So like, wait, Griffin, I'm teaching class.
Eating my apple.
I know he's eating your apple. Go get another apple then. Close the door.
Daddy, I did my homework.
Sorry. All right, go close the door, okay?
Okay.
I got to teach the class right now. Sorry. I've got two of my kids here. Sometimes working from home is a lot easier, but sometimes it's not. It's harder to teach class from home, I'll tell you that. It's easier to grade things. All right. So you have certain kinds of things going through the cell, and you have certain things being blocked outside of the cell. And the cell membrane kind of makes up this barrier that says this is the property of the cell. Just like how your front door makes up a barrier, even though it's not very thick. You know, like the front door might be thick, but the wire, the screen door might not be very thick at all. And that makes up the barrier that allows things in and out. It says this is the boundary of the cell. So, there's two types of transport that allows things in and out of the cell. One is called passive transport, and the other one is called active transport. Seamus, all right, can everyone else hear? Can everyone else hear, like, relatively okay? All right. Seamus, you might have to log out and log back in. I can't type very well. Let's see. All right, the difference between the passive transport and the active transport is basically energy. It's the amount of energy being used. Let me show you a simulation and see if it makes a lot of sense this way, okay? This is the one. All right. Can you guys see the computer screen, the membrane channels that I have? Okay. The what you call it, the simulation might be glitchy, and I'll send you guys the link so you guys can try it at home, but I'll explain to you what's going on. All right. What I'm going to do is I'm going to put a bunch of these blue diamonds inside of here. I'm going to click this thing 20 times. All right. And then I'm going to play it. So I know it's glitchy, but what you have here is you have these blue molecules, whatever they are, on the bottom part of this thing. Okay? I can show you the concentrations, and you can see that the blue diamonds are, more. There's more of them, and I know it's glitchy, but I mean, you can basically see what's going on, right? All right. So what I'm going to do is I'm going to open up these channels. I'm going to open up the screen doors for these blue particles to go through. Here's my question to you is, over a long period of time, will all of the blue particles over here go to the top? If I wait long enough, will all of the ones on the bottom go to the top? If I open up some of these membranes? Yes or no? Jonathan says yes. All right, Ciara. Okay, everyone's saying yes. Everyone agrees? Seamus says no. All right. Here's my question is why? Why is it no? And actually, Seamus, you're right. All of the blue ones on the bottom won't go to the very top. Why is that? If I open these up, let's open up the channels. So I open up these spots. So you got some of them going. But will all of the blue ones go to the top and then the bottom part will be completely clear? Is that that's what I'm asking you? No. What's going to happen? No, they won't get stuck. They'll pass right through the blue passages. But what's going to happen? If I have 20 on the bottom, will all 20 go up on top? Or will I eventually, if I wait long enough, what would you say will happen? No, all of them will not fail. Okay, would it be safe to say that if I have 20 on the bottom and only the bottom, and then I let the thing go for a little bit, then eventually I will have roughly 10 on the top and 10 on the bottom. Half of them will be on top, half of them will be on the bottom. Is that fair to say? And that makes sense to you, right? Like, I don't understand why it would be that, you would get more on top than on the bottom. Now, you might have 11 on top and 9 on the bottom. Okay. And you might also have vice versa. You might have a little more on the top or a little less on the top and a little more on the bottom. But on average, you'll have half of them go on top and half of them go on the bottom. Which you can see here. You look at these concentrations and you can see that it started off that the blue bar was all the way up over here and there was no blue bar over here. And now they go back and forth to being about the same size. Does that make sense to you? All right, here's my other question. What happens if I add a bunch of blue particles on top? So I'm going to click this button a couple of times and it's going to throw in a few more of these blue particles. What would you say about the concentration Actually, you know what? Let's close this out. All right. So right now they're about even. Got it? So I'm going to add in a few more. What can you tell me about the concentration of the top compared to the bottom? What can you tell me about the concentration of the top compared to the bottom? I apologize for being glitchy. I'm doing the best I can. What can you tell me about the concentration of the top compared to the bottom? Can you guys hear me? All right. So the concentration on top is much higher than the concentration on the bottom. Do you agree? There are more blue particles on top than there are on the bottom. Now, when I open up the gates, what's going to happen? When I open up the blue gates, what's going to happen? Seamus says go down. I agree with him, but be more descriptive. Now, say that we're looking at you can think of these as like ice skaters, and we're looking down on this. But what's going to happen to the blue ice skaters on top when I open up the gates for them to go through? There's 2 ice skating rinks over here. They might stay or they might go, but what will happen to them eventually? What would you say? Are all of the ones on top going to go to the bottom? Will they go half again? Half. Exactly. Yes, they will go half again. If I open up the gates, the particles will flow from the higher concentration to the lower concentration until eventually they have exactly the same amount on each side. On average, of course. Does that make sense? So, particles will often flow from the higher concentrations to the lower concentrations, and that doesn't require any forcing, anything that's being forced happening here. You get that?
Our vehicle's ready for pickup.
Okay, awesome. All right, cool. So let's pause this and let me talk to you a little more about it. So that's what passive transport does. And that process is called diffusion specifically. Diffusion happens when substances from a higher concentration moves to a lower concentration. I apologize for the glitchiness. Let me explain that again. Diffusion happens when things go from a higher concentration to a lower concentration without any energy being needed for the process to happen. It didn't take me to do anything to it for that to happen. Are we cool with that? Now, I'm going to try to finish this off quickly just because the glitchiness of the microphone is a little bit frustrating. But let me explain to you what active transport is. You might want to read up on this facilitated diffusion paragraph, and it's really quick. Well, basically, the facilitated diffusion are like, I guess I think of them as holes inside of the screen door for specific things. For example, if you have a dog, then in your screen door you also have a doggy door, right? You also have a hole that's bigger that allows the dog specifically to go in and out. Now, if it were just an open hole, that would be like a channel protein, which is a hole that allows things to go in and out. Whereas if it were a hole that has a door on it, a flapping door, then that would be more like a carrier protein. And that's kind of the difference between those two. Does that make sense? All right. Here's the next question I have. Here's the last question I have. Let's go back to our thing. What if I wanted to get everything out of the bottom here and put all of these blue particles into the top? What would I have to do? Okay, I'd have to open the gates, obviously. I'll open all the channels. The green ones won't make a difference because the blues can't pass through the green. But what happens if I wanted to clear everybody out of the bottom ice skating rink because, say, I need to like sweep the ice? And so I take everyone from the bottom and I want to put them in on top. I would have to use force exactly. I would have to get some security guards and kick them off the ice. Everyone on the bottom skating down here, I would have to kick them off, and I would have to say, everyone has to get out. Does that make sense? See, moving from a higher concentration to a lower concentration doesn't require anything of me. It doesn't require any force whatsoever. That's why it's a passive transport. But moving from a lower concentration to a higher concentration, there's an ambulance. That requires something funky to happen. That requires some force to be used, some energy to be used. If I wanted to clear out this bottom part, I would need to use some kind of energy, as in the form of a security guard. And what that is doing is that's called active transport. And that's the difference between the two. The passive transport, you don't need to do anything to it. Whereas the active transport, energy needs to be used in order to accomplish something that you want to happen. Does that make sense? So, sometimes there's certain nutrients that we would want to take into our cell. But we can't get those nutrients in because there's no nutrients inside of our, because we can't take in those nutrients because the diffusion process won't happen because we're trying to go from a lower concentration to a higher concentration. And so what happens is we need to use force to get those nutrients into that cell. And that's where active transport takes over. Are we cool with that? All right, I apologize. I didn't get through nearly as much as I wanted to. Let me just lecture for 5 more minutes and then we'll finish. So there's these two different types, there's many different types of active transport. An additional two that I want to tell you about is endocytosis and exocytosis. Endocytosis is one form where what happens is a particle will come in from the outside, and the cell membrane, what it will do is it will form a protective barrier around that particle. and then it will suck that thing in. That's called endocytosis. Endo being kind of the idea of, I don't know, when I think of endo, I think of something becoming inside. Exocytosis, okay? Exocytosis, on the other hand, is one way that we can get waste products outside of the cell. Some of these things are too large to go through our screen door. So what we do is we have it wrapped up inside of the cell membrane, and then that cell membrane will join with the cell membrane and then kick out these different particles that might be inside of our cell that we don't want inside of there. So we're kicking it out. Does that make sense to you? And then exocytosis makes sense to me because I think of exo as like an exoskeleton, the outside of something. Exoskeleton is your protection on the outside. So it's the process of kicking something out. All right, the last thing I want to tell you about is why are cells so darn small? That's my question. Why do they have to be small? Like, for example, when we grow up, do we grow up and the cells that we have when we were a baby, well, the cells that we have when we're a baby, do we have, do they just grow larger? Or do we take, or I mean, since we're getting bigger because we're growing up, we just have more? Adults have more cells than babies do. Yeah, they just have more. Okay, they don't change size. They're still the same size. The size of the cells inside of my body are the same size as the cells inside of my 3-year-old. I just have a whole lot more of them. Now, why? Why don't cells grow bigger? Why do they have to be a certain size? And the reason being is because it's actually a math thing. Think of a box. All right, can you envision a box in your head? Now, what we want is, all right, since it's so close to Christmas time, I guess this would be an appropriate question. Let me ask you this. Do you understand what I mean by saying the volume of something? The volume of a box? How do you find the volume of a box? The volume is 3? No. How do I find the volume of some kind of box that I have? All right, it'd be the length times what? Good. Length times width times height. Exactly. That's how you find the volume of something. Got it? Now, do you understand what I mean when I say surface area? The surface area would be like, how much wrapping paper would it take to cover this box? Does that make sense? How much wrapping paper does it require to cover this whole box? Now, what you want in a cell is you want the volume to be very small compared to the surface area. The reason being is because it would allow a lot of nutrients to flow in and out of the cells if it has a large surface area. If it requires a lot of wrapping paper, but it doesn't hold a whole lot of stuff, that means there's a lot of area for that thing to be able to move nutrients in and out of the cell. Here, let me give you an example, okay? You guys ever eat shave ice? Okay. Now, on the shave ice, they have the big block of ice, right? They got the big block of ice. Now, I'm going to ask you this. Imagine they have two big blocks of ice at the Shave Ice, store that you guys go to. And they grind one of those blocks into Shave Ice, really small. Okay? And then they keep one of the other blocks as a whole cube, a giant big cube of ice. So you have one of the blocks is ground down to Shave Ice, and the other one is a big cube of ice. Now they throw everything inside of a big bathtub full of water. Which will melt first? The one that's all cut up into Shave Ice, or the one that's a big cube of ice? The shaved one. Why is that? I agree with you guys 100%, and I don't think anyone disagrees with me. Because it has tiny holes? Well, if you think about it, if it's smaller, if the Shave Ice particles are smaller, it has more surface area to touch the outside water. And touching the outside water is what causes it to melt. Does that make sense? So even though I have the same identical two blocks, the one that's all cut up into Shave Ice will definitely melt faster. And the reason being is because it has more area touching the water that's causing it to melt. Whereas the big one doesn't have much surface area as compared to the small one. Does that make sense? You're going to leave pretty soon. Let me just finish this last topic I have, okay? So what you want in a cell is for the volume to be smaller than the surface area. And not only that, but you want the surface area to be much bigger than the volume. So, let me show you some math, and I'm just going to show it to you. I'm not going to ask you to calculate it. If I have a cube, an ice cube, that is 1 millimeter by 1 millimeter by 1 millimeter, the sides are each 1 millimeter big, then the surface area would be 6 millimeters squared. But the volume would only be 1 millimeter cubed. So you don't get much of a volume at all, but you get a large surface area. Now let's say I had another cube that is 4 millimeters by 4 by 4. The volume would be the length times the width times the height, so that would be 4 times 4 times 4, giving me 64. That's a big volume. And the surface area would be 96 millimeters squared. Now you're thinking, wait a second, isn't this surface area bigger than this one? Yes, we're going to have a lab on Wednesday where we're going to do photosynthesis. But let me finish this. Isn't this surface area over here bigger than this one over here? So wouldn't it be better to have a bigger, wouldn't this be better to have a bigger molecule? And then my answer to that is, well, look at this volume compared to that volume. If I were to take this surface area and divide it by that volume, I would end up getting something like 1.5. Whereas if I were to take this surface area and divide it by that volume, I would get 6. So your ratios are bigger if you have smaller things, which is why cells have to be so small. Because what that does is it makes the surface area huge compared to the volume. If it were a big volume cell, it would need too much nutrients to move in and out, and it wouldn't have enough surface area to allow enough membrane, cell membrane, so that things can move in and out. It would require too much energy. That's what I'm talking about. Does that make sense to you? I think that's an important thing to know. Yes, I am recording this. I apologize for it being glitchy today. But class is done. I kept you guys 5 minutes over. I apologize. I think I had to go a little bit over time just because I had to slow this class down. I only got through half of what I wanted to cover. But I think it's good stuff. All right, go say goodbye. You got to go to the bathroom, I guess. Sorry, I'm talking to my 3-year-old. All right, I'll talk to you guys later.